Okay, let's talk about electricity. It's this invisible force that powers, well, everything in our lives, right? From the phone in your hand to the lights above your head. But here's the thing. Even though we use it every single second, how many of us actually understand the fundamental rules that make it all go? Well, that's exactly what we're going to break down right now.
I mean, look at this. It powers our entire world, from the super complicated circuits inside your phone to just, a simple lamp on your desk. It's all running on the exact same basic principles. But how does that invisible energy actually do it? How does it flow from a battery, snake through all those little parts, and actually get work done? That's the mystery we're going to solve today.
And believe me, getting this right is absolutely crucial. There's this great quote, "Weaknesses in voltage, current, and resistance will cost you." And it's so true. If your understanding of these basics is a little shaky, it can cause all sorts of problems down the line. So our goal here? It's simple. Let's build a rock-solid foundation, and I promise, everything else is just gonna click. All right, so to really get electricity, you only need to meet three main characters. Seriously, just three. Let's think of electricity like a river of energy, okay? So our three characters are gonna be the pressure pushing that river, the speed of the river's flow, and of course, anything that gets in its way.
First up, we've got voltage, and we measure it in, you guessed it, volts. This is our pressure. It's the electrical potential difference. Just waiting, ready to push those electrons through a conductor. It's the oomph behind the flow. Simple as that. No voltage, no push, and nothing moves.
And wow, this electrical arc is a perfect way to visualize it. The potential difference, that voltage, between these 2 points is just so huge, the pressure is so high, that it can literally force electrons to jump right through the air itself. That's pure voltic in action. It's potential energy just being unleashed.
Okay, next up is current. We measure this one in amperes, or just amps for short. So if voltage is the pressure, then current is the actual flow of our electrical river. It's how we measure how many electrons are moving past a certain point every second. This is the electricity actually doing its thing.
And that brings us to our third and final character, resistance, which we measure in ohms. Resistance is pretty much what it sounds like. It's anything that opposes or slows down that flow of current. So back to our river analogy, this is like a narrow part of the pipe, or maybe some big rocks in the riverbed. It's basically the friction in the system.
So there you have it, our three characters, the push, the flow, and the opposition, voltage, current, and resistance. But here's where it gets really, really cool. They aren't just doing their own thing, nope. They are all connected by one simple, elegant, and unbelievably powerful rule that governs, well, everything. And this is it, V equals I times R. Ohm's law. That's the whole thing. It just means that voltage is always equal to the current multiplied by the resistance. This one tiny formula, it's the absolute foundation of pretty much all electrical calculations. It tells us exactly how our three characters are going to behave every single time. No exceptions.
And you know what the best part is? You do not need to be a math genius to use this. It's super easy to just rearrange the formula to solve for whatever you need. So say you need to find the current, just cover up the I and you're left with voltage divided by resistance. Need to find resistance? Cover the R and it's voltage divided by current. It's just a simple but super powerful little tool.
Okay, but listen up, because there is one critical rule you have to follow here. And this is hands down the most common mistake people make. Whatever values you plug into Ohm's law, they all have to refer to the exact same part of the circuit. You can't mix and match. So for example, you can't just take the total voltage of a whole circuit, say 12 volts, and use it with the resistance of just one little resistor in that circuit. It doesn't work. You have to use the voltage across that specific part with the resistance of that same part. If you can remember that one thing, you're golden.
Okay, so we've met the characters, we know the main rule. Now let's look at the two basic ways a circuit can actually be laid out. The way to think about it is this. Our river of energy can either follow one single winding path, or it can split off into a bunch of separate streams.
And this diagram just breaks it down perfectly. So over on the left, you've got a series circuit. See that? It's just one single loop. The current only has one path it can take, kind of like a one-lane road. But then on the right, you have a parallel circuit. Look at how the path splits up. It gives the current multiple branches to flow through before they all meet up again. And here's the kicker. The rules for how our big three, voltage, current, and resistance behave are completely different depending on which setup you're looking at.
So here's the really key difference you need to remember. In a series circuit, the current stays the same everywhere, but the voltage gets divided up among all the components. In a parallel circuit, it's the total opposite. The voltage is the same across every single branch, but now it's the current that gets split. The easiest way to remember? Series means same current. And you've seen this in real life. Think about those old cheap holiday lights. One bulb burns out and the whole string just dies, right? That's a classic series circuit. The one single path has been broken, so everything stops.
All right, so we've covered a lot of the theory. Let's bring this into the real world. You know, the electricity that's powering your laptop right now is actually a different kind of electricity than what's coming out of the socket in your wall. It all boils down to two main types of current.
First, you've got direct current, or DC. Think of this as that calm, steady river, just flowing in one direction. This is what you get from things like batteries or solar panels, and it's perfect for all our delicate electronics. Then you have alternating current, or AC. This is more like a tide, constantly and rapidly reversing its direction, back and forth. This is what comes from the utility grid, right out of our wall outlets, and it's amazing for powering big, heavy-duty stuff like motors, heaters, and HVAC systems.
And you know what's so amazing about all this? It doesn't matter if you're talking about the tiny 1.5 volts from a single AA battery or a massive 480-volt industrial panel like this one. The fundamental rules we've been talking about, voltage, current, resistance, Ohm's law, they all still apply. The scale might be completely different, but the physics, it's exactly the same.
So let's just bring this all home. When you boil it down, it's actually a pretty simple story. Voltage is the push, current is the flow, resistance is the stuff that gets in the way. And Ohm's law, that beautiful, simple equation, that's the rule that connects all three of them, every single time. That's your foundation.
So we've just spent all this time learning the rules that electricity absolutely has to follow. But that leaves us with one last really fascinating question. What happens when you try to break those rules? For instance, what happens when resistance suddenly drops to almost nothing? Well, that's where things get really interesting, and it's a story for another time.